Good day. My name is Dick Jackson, and I'm presenting this with Lauren Madronich and Robert Walsh of Geofirma Engineering. The topic is the hydrogeological challenge of geological CO2 storage in the Ontario Cambrian Formation. It is important to understand that geological CO2 storage is proven to work in Cambrian sandstones in Canada. Since 2015, there have been 2 projects in Western Canada that have demonstrated this. The Quest project, shown in the upper photograph, showing the carbon capture unit at the Shell Canada refinery in Fort Saskatchewan, and the Aquastore project that is associated with the Boundary Dam power plant of SaskPower near Estevan, Saskatchewan. Regarding Quest, it has a capture capacity of about 1 million tons a year and has been operating since 2016. The CO2 is transported by pipeline as a dense fluid 65 kilometers north to 3 injection wells, 2 of which are operating at any one time with an injectivity of greater than 150 tons per hour. The geology at Quest is that of the Alberta Basin, so a very thick sequence going to over 2 kilometers in depth before the Precambrian is encountered. The reservoir is the basal Cambrian sands at 2,200 meters with a porosity of 17% and a permeability of about 1,000 millidarcies. The cap rock are a bunch of shales overlain by the Lotsberg salt, a quite excellent cap rock. Monitoring wells are much higher. They're in the Cooking Lake Formation at 1,360 meters below ground surface, about 800 meters above the reservoir. The biggest challenge in southwestern Ontario is that the geological storage potential reservoir is some distance from the emission sources that are spread from Sault Ste. Marie to eastern Ontario. But they are in particular clustered around Hamilton, Nanticoke, and the Sarnia-Lambton area. These emission sites emit about 24 million tons of CO2 a year. Probably by 2035, this will be down to about 10 million tons of CO2 a year due to fuel switching and electrification. Geological storage of CO2 or sequestration will follow the CSA guidelines. That means that it would be at depths greater than 800 meters to allow a maximum pressure at the injection level of greater than 9 megapascals. It must be sealed by competent cap rock with minimal groundwater inflow from surrounding rock. Preferably, the reservoir will be near major CO2 emitters and pipelines, preferably penetrated by few oil and gas wells, particularly legacy wells, that will require plugging. And preferably, there will be a large pore volume available for CO2 storage or sequestration, so there will be a limited delta pressurization in the reservoir. Preferably, there will be few critically stressed faults that might slip with fluid injection, producing microseismicity. Well, what do we have for geological CO2 storage reservoirs? Essentially, we are confined to the saline Cambrian aquifers along the north shore of Lake Erie and offshore as well. Unfortunately, these are of unknown hydrogeological and geomechanical properties. Depleted oil and gas fields, particularly those in the Cambrian, are potential reservoirs, but of course these are penetrated by large numbers of legacy wells, and the fields are of limited storage volumes. Enhanced oil recovery may make these financially attractive for some storage, and there will be the problem of induced microseismicity. Cambrian sandstones are exposed in outcrop in eastern Ontario and of course overlying the Precambrian basement. They are given here names that are more suitable to Eastern Ontario and Quebec. There are somewhat over 100 existing wells that fully penetrate the Cambrian to the depth of the Precambrian basement. Fortunately, in the area of greatest interest, which is Heidelberg, Norfolk, there are relatively few of these wells. The depth to the Cambrian in the area just discussed, Heidelberg, Norfolk, and essentially from Niagara to Long Point, is generally greater than the 800 meters, considerably greater in some parts, required by the CSA guidelines, typically of the order of 950 to offshore over 1,200 meters below ground surface. The isopack of the Cambrian shows that from Long Point to, say, Dunnville, the potential prospective storage reservoir is of about 70 to over 100 meters in thickness. Here is one cross-section through a 75-meter thick section of the Cambrian along Lake Erie. You can see a depth. It is coarse or medium sandstone. It shallows into beds of sandstone and dolostone, and therefore becomes of more limited use as a reservoir because the dolostone is relatively tight. These histograms present the petrophysical data. You can see it's a multimodal distribution of porosity and permeability. The high porosity and high perms are associated with the sandstones, and of course the low porosity and low perms associated with the dolostones. Mean permeability is around 40 millidarcies, but it can be over 100 millidarcies in the lower sandstone units. The caprock is extremely tight. Geofirma measured these caprock vertical permeabilities during its work at the Bruce nuclear site about 15 years ago, and typically the vertical permeabilities are less than 10 to the minus 5 millidarcies, essentially impermeable. That caprock and the saline sandstone reservoir are shown in this figure, illustrating an injection well and the radial distance away from that injection well that we'll be discussing in the next few slides. Immediately around the injection well, the near well region, there is single phase CO2 flow with very large pressure gradients and the drying out of the brine by evaporation under the particular temperature pressure regime there. This is going to cause salt precipitation that will have to be dispensed with, typically by warm water flushing every year or two. Beyond that near well zone is a zone of two-phase brine and CO2 flow in which both viscous fingers and thief zones, dependent on heterogeneity, develop. You'll notice that because the CO2 is of low viscosity and buoyant, with respect to the brine, it rises to the base of the Ordovician caprock, which we have just looked at. The injection of CO2 displaces and elevates the brine within the saline storage reservoir. Therefore, in the upper figure here, you can see the supercritical CO2 injected in the injection well, a zone of CO2 displacement with CO2 brine mixing at the front of it, and the brine being displaced radially away from the injection well. The lower figure shows the pressure away in radial distance from the injection well, and it drops off, as you would expect, as the radial distance increases. But even out to a distant radius, there is still a formation pressurization increase, which we will refer to as delta P. Robert Walsh in Ottawa has numerically simulated this kind of flow of CO2 within the brine saline reservoir. Here is the conceptual numerical model with its boundaries. It is a radial model, and we'll just look at one direction, one slice of that model. We have injection of CO2 into the injection well here, a reservoir thickness of H with permeability K and porosity phi. The pressure, temperature, and salinity and the mole fraction of sodium chloride within the reservoir is specified. We will now look at migration of CO2 and the pressure plume away from the injection well over a 20-year period. On the left of this figure, which shows the discretization and assignment of formation porosity to the model layers from 8% in the blue up to 16% in the yellow and orange, we have the depth of the fully penetrating injection well into sandy materials at the bottom and increasing amounts of dolostone above that sandy material. Similarly, for permeability, the discretization is as shown. The dolostones are given a low horizontal permeability of 25 millidarcies, while the sands have in excess of 75 millidarcies. The top of the model is the Ordovician. The bottom of the model is the Precambrian. And you can see that this model will take us out over a period of 20 years, a distance of 35 to 40 kilometers. We now show the base case results after 20 years of injection. Delta pressurization at the well itself is 8 MPa. The upper figure shows the breakthrough of CO2 after 20 years. You can see the farthest extent is around 2 kilometers, and the saturation there is probably only the order of 30%. Lower, in the lower figure, you can see the delta pressure plume, which has migrated much farther. The pressure plume is out about 5 kilometers. On the far right are small figures showing the amount of CO2 injected over 20 years, just under 10 million tons, and the delta pressurization with distance going from approximately 8 down to 0 MPa at 30 kilometers. We now show the base case simulation of the CO2 mass stored or sequestered and the delta pressurization after 20 years of injection. On the left-hand side is the figure we just discussed, the mass of CO2 injected over 20 years, just under 10 million tons. On the right, we're showing the delta pressurization with distance. This is really the controlling factor in CO2 injection because, as you can see here, delta pressurization goes out far farther. It follows this curve than the CO2 plume, which goes out about 2 kilometers after 20 years. Now, we're going to define an area of regulatory review as that area that experiences a 2 megapascal pressure increase, and that goes out to about 7 or 8 kilometers. So within that area of regulatory review, we could expect to have to undertake very careful 3D seismic and examination for potential faults and legacy wells. In other words, this is where we would perceive the greatest potential for leakage would occur out to that about 8-kilometer distance. This is for 20 years injection at just under 10 million tons. The extent of travel of the delta pressurization front is very much an effect of reservoir compressibility, which is a function of natural gas saturation on the CO2 mass stored, and particularly the delta pressurization, after 20 years of injection. Here, note that the injection pressure is the same for all three scenarios. But what we've been showing you has been the base case, with brine only shown. And that's the bottom line here, just under 10 million tons injected. That's this curve here, with the area of review going out about 8 kilometers. If we make the brine with 2% natural gas saturation, 98% brine, 2% gas, then the area review falls to around about 5 kilometers. If we give it as much as 10% gas saturation, 90% brine, then it falls even further, and the area review, being the 2 megapascal limit, is down to about 3 to 4. So what we learn here is that compressibility is hugely important. That can only be tested by a 2-well hydraulic test in situ, and that depends on further drilling and testing. The Battelle Research Institute in Columbus, Ohio has done a lot of work for the U.S. government on CO2 sequestration in the Midwest, and it developed this nomogram with injectivity rate on the ordinate here in tons of CO2 injected per year for a given pressure increment versus the transmissivity to CO2 of the formation. Transmissivity here, as in hydrogeology, is permeability times thickness, although we're dealing with permeability, not hydraulic conductivity. And you can see on this figure how good an injectivity zone is present at the Quest site in Alberta. Much better than the 2 Midwestern sites that were considered by Battelle. The Aquastore site in Saskatchewan is relatively poor, having a much lower injectivity than Quest. Now, if we plot prospective basal Cambrian storage targets in eastern Canada, what we see is Haldeman comes out relatively high, Essex 2, Elgin lower because of the thickness and lower thickness, and St. Lawrence Lowlands, the Potsdam in Quebec, is the poorest of all these shown. And that's principally because of its very low permeability. So you can see we have some prospectively decent reservoir. Well, there are risks, of course, and the public will want assurance that CO2 will remain sequestered. As long as we don't have faults in legacy wells, I think that is a given because of the quality of the Ordovician cap rock. But there will be faults that we will have to discover by 3D seismic and drilling and testing, and there will be legacy wells that will likely require replugging. There almost certainly will be induced seismicity. We know that, but it won't necessarily be strongly felt. All these will have to be evaluated. In conclusion, the saline Cambrian aquifer of southwestern Ontario is a prospective reservoir for geological CO2 sequestration along the north shore and offshore of Lake Erie. It is poorly characterized with respect to geomechanical and hydrogeological parameters that control injection and storage of CO2. Little is known of the structural features such as faulting, stresses, and regional facies changes, and the potential for induced seismicity. The injectivities, i.e. the injection rates per well, and formation geomechanical responses are the determining factors in the operational storage of CO2 in reservoir rocks. Injectivities in the basal Cambrian will likely be only 200 kilotons per year per well. Therefore, 5 such wells will be needed to match the injectivity of the Quest injection facility in Alberta. Therefore, around 50 injectors will be needed to store just 10 million tons of CO2 a year, which is likely to be the amount of CO2 requiring storage in southwestern Ontario by the year 2035. Thank you very kindly.